Good evening, everybody, and welcome to this webinar hosted by FEMA, the Federation of European Motorcyclist Association, in collaboration with MIPS. My name is Olea Karlsvik, and I am the president of FEMA. Today, I'd like to give you a brief overview of the work we do for motorcyclists, how we operate, and why it's important for riders to get involved in their national motorcycle organization. FEMA and its national members organization work every day to protect the rights, safety and freedom of motorcyclists across Europe. We monitor legislation, technical standards, licensing directives and transport policies, both nationally and at the EU level. We participate in hearings, meet with authorities and technical committees, and we collaborate with researchers and industrial experts. Our goal is to improve infrastructure, ensure fair treatment of motorcyclists in traffic, and secure the motorcycle's place in the future of mobility. Our work is built on knowledge, on collaboration and grassroots engagement. We collect input from riders, analyze accident data and trends, and use this to influence decision makers. We are present where decisions are made, whether in Brussels, national transport ministries, or at the local road safety event. But we are also a movement of riders, and that's where you come in. As a motorcyclist, you have a voice, and that voice becomes stronger when you stand together with others. By joining your national motorcycle organization, you support the fight for a better safety, fair policies, and respect for motorcyclists. If you're joining us today and don't have a national motorcycle organization in your country, you can still support our work. Visit FEMA-motorcycle.eu to learn more and consider making a direct contribution to support our mission. By joining us, you gain access to information, a community, and the opportunity to make a difference. Your voice matters, our mission needs it. Before we continue, it's my pleasure to welcome our guest speakers from MIPS. First, we'll hear from Max Strandwich. He's the CEO of MIPS and board member at sensor technology company Quintessential Design. Max will introduce the foundation of MIPS and share the company's vision for head protection. Then we'll hear from Madeleine Falstedt, a biomechanical specialist at MIPS and member of the technical committee for head protection at CEN. Madeleine will explain how the head and brain are affected during an impact, the purpose of the MIPS safety system, and give us an overview on how motorcycle helmets are tested and certified today. We appreciate your commitment. Every voice matters, and with yours, we are building a safer, stronger riding community. So thank you for joining us today. Now, I would like to hand over to Max and Madeleine. Thank you.
Good evening, everyone. My name is Max Strandwich, and I am the CEO of MIPS. With me today, I also have one of our biomechanical specialists, Madeleine Falstedt, and the two of us will take you through today's webinar. You will have the possibility to ask questions, and of course, we do that after the presentation. So if you want to ask a question, please enter your question into the chat web box. So, of course, if we first start with MIPS, who are we? We are a company that originates out of Sweden. We are world leaders when it comes to helmet-based safety. We partner around with helmet brands all around the world, and to include our MIPS system, our safety system, into their helmets. A lot of companies and people think that MIPS do helmet. We do not do helmets. We do a safety system that is included into helmets. So today you will hear us talk a lot about rotation, and rotation is probably something that you don't go around think about every day in your everyday life. And of course we will explain what it is. So first of all, talking about rotation, the brain is very sensitive to rotation, and that was something that was recognized already back in 1940. Yet, when many helmet manufacturers are designing their helmets today, they focus more on linear performance versus rotation. And of course, these are complicated subjects, and we will explain a little bit more on what we mean with that later in the presentation. This is a subject that is very close to our heart, something that we have been focusing for almost 30 years about. And of course, something that we are probably the most knowledgeable about in the helmet industry. This work has, of course, resulted into a safety system for helmets, which is designed to help redirect rotational motion away from a head. If we start with our vision, of course, the most important, why do we do it? So, of course, our vision is about reduce head injuries and save more lives. That's why I do it, and that's why most people work at MIPS. Having that vision is, of course, fantastic and something that sits in our DNA. If we look at the company as such, it started almost 30 years ago with a very frustrated neurosurgeon. He had a lot of patients on his surgery table that suffered from traumatic brain injury, despite the fact that they actually had a helmet on their head. And he started to do a lot of research. He quickly realized that he cannot solve the problem alone. So he teamed up with two biomechanical experts at the Royal Technology Institute in Stockholm, and they started the foundation of the research that we have done on the subject in MIPS. Today, of course, we have more than 50 engineers that is focusing only on brain protection systems. We have 5 PhDs. And of course, like I said, probably one of the most knowledgeable in the area in the helmet industry. Our technology has, of course, been validated by third-party testing. We, of course, never stop. We continue to develop, continue to do a lot more research. We are working with the Royal Technology Institute in Stockholm, but also with the key universities around the world to, of course, always to better understand the subject, but of course to continue to develop. Today we are presenting from our test laboratory, which is probably the most advanced in our area in the world. And of course, we also have state-of-the-art capabilities when it comes to computer simulation and modeling capabilities within the area. And of course, like any responsible company, we have also a very strong sustainability commitment. What does that mean, and what kind of position do we have on the market today? Today we are partnering up with around 150 different brands. Our head office is outside Stockholm in Täby, where we have most of our employees. We have since inception put around 1,000 different helmet models equipped with the MIPS safety technology system. Since inception, we have sold about 50 million units. We, of course, are a very IP-heavy company, and we have more than 400 patents worldwide and more than 50 patent families in the technology that we address. If we then look at what or where are we present today, you can find MIPS in 9 different subcategories, all of them with one common thing, and that is, of course, in sports or areas where you're normally exposed to rotation or oblique impacts. Today you can find MIPS in bicycle helmets, climbing helmets, helmets in industrial safety, equestrian helmets, law enforcement, armed forces, motocross helmets, motorcycle helmets, ski helmets, and team sports. So a lot of areas, all with the common thing that you are exposed to rotation in those areas. Then, of course, now we will go into the real juicy part of the presentation, diving into our world of science. And of course, there is no one better to do that than Madeleine, who will take you through our science background and how we validated our technology.
Thank you, Max. So yeah, I will take you through the background, the scientific background to MIPS. First, a short message from our legal team. So, when we talk about head injuries in motorcycle accidents, what we see is globally around 30% of all road fatalities are with power 2 or 3 wheelers. We see that this is a higher percentage of fatalities in Asia compared to Europe, where we are below 30%. But roughly it's around 3,000 fatalities in Europe every year due to motorcycle accidents. And we'll look into this accident when we have more severe injuries or fatalities. The injuries are often to the thorax, to the head, or to the lower extremities. And among the most common injuries are to the head and cerebral concussions. I will come back to concussion and explain that a little more. But first, I would like to introduce you to one term that Max already mentioned, and that is oblique impacts. I don't know if everyone knows what an oblique impact is, but think that you are sitting on your motorcycle, you're riding it, and you have a fall, maybe to the side. You will then not fall straight downwards. You will fall toward the side, but also downwards. So this means that the impact will be with an angle, and that is what we call our oblique impact. And in these oblique impacts, you will have could have a rotation of the head. And we have mentioned rotation quite a lot. So why are we mentioning rotation so much? So we should think about the brain as water, because the brain has a high content of water. And I will show you with this snow globe. I will show you first a linear impact, meaning that you have little rotation induced, thinking that you're falling straight towards the ground and impacting the ground, compared to if you have this oblique impact that I explained on the previous slide, where we induce rotation. So let's look at the snow globe that is filled with water and should represent a simplified example of the brain. So if we play the video here, we see the linear motion. And then we see when we rotate it. In this first, when we have the linear motion, we don't have much deformation of the water. You don't see the snowflakes coming up as you do when you're inducing rotation. You see more deformation of the water, snowflakes comes up from the bottom of the snow globe. And this is what happens inside the brain when you're having an impact. Linear, not so much deformation of the brain tissue. But when you're using rotation, more deformation, and this deformation can be can cause damage to your brain tissue. And if we look into different types of brain injuries, we see when you have this linear motion and not so much rotation, we have mainly injuries towards the skull, such as skull fracture or bleedings that are caused by the fracture, such as epidural hematoma and contusion close to the surface. If we then induce rotation, as we have when we have oblique impact, we can sustain more injuries towards the brain, such as concussion. As I mentioned, that was one of the most common injuries in motorcycle accident. We also have subdural hematoma, this means that in the brain you have two hemispheres, and between these two hemispheres you have vessels, blood vessels going in between. And if they rupture, you can have a subdural hematoma. And then we have diffuse axonal injury, also injury to the brain. And now, in a simple way, I will explain this as a more severe case of a concussion. So, today, or until recently, when you evaluate the helmet in the helmet standard, you use this linear impact, and a standard is a way for the helmet manufacturers to be able to sell the helmet on the market. If you haven't passed the helmet standard, you cannot sell the helmet on the market. So the helmet manufacturer designed the helmet based on this linear impact, because that was the standard was evaluating the helmet for. So more looking into injuries to the skull. But now, recently, also oblique impact has been introduced into the standard, and this is how it's evaluated in the lab. So you're dropping the helmet with the head form against the angled surface and measuring both the linear motion and the rotational motion. And this is what I have explained before, that you impact the ground with an angle, but in the lab you are doing it by a drop against the angled surface, but you're measuring the same thing. So this is a new thing within the standard. But we should also remember that a standard is just the minimum requirement. And so this is what the helmet manufacturer need to pass to be able to sell the helmet on the market. It doesn't say if it is a good or less good helmet, it's just that it has passed the minimum requirements. So I would just like to show you an example here also. So here you look at statistics of motorcycle accidents. So the solid bars, you see riders that was wearing a helmet, and the striped bars, you see riders that didn't wear a helmet. This data is from US. And we can see then that we have both skull fracture and traumatic brain injury, TBI. And we see that the helmet reduces the risk both for skull fracture and traumatic brain injury. But we see also that the reduction is larger when wearing a helmet for skull fracture comparing to traumatic brain injury. And this is explained by how the helmet manufacturer has designed the helmet. So a lot of focus on this skull fracture and the linear motion. And it's here where MIPS come in to place, where we also focusing on the brain and introducing a system that will try to redirect rotational energy so it's not transferred to the brain that is sensitive to rotational motion. And the idea actually comes from the human anatomy. So in the human head, you have the outer skull and then the inner brain. And in between here, you have a fluid which makes it possible to have a relative motion between this. And our idea with the MIPS safety system is also to have a relative motion, but instead we have the relative motion between the head and the helmet. So we try to design our safety system so we have a relative motion between 10 to 50 millimeter, and it shouldn't depend on where on the head you're impacting or which direction the impact comes from. So it should be omnidirectional system. So I would like to show you a short video explaining the system. So you will see here a motorcyclist with a helmet with MIPS technology impacting the ground. And you will see here in the yellow layer that you have a relative motion between the head and helmet. So the head is not rotating as much as the helmet because the rotational energy is redirected away from the head. I mentioned that we will try to achieve a relative motion of 10 to 15 millimeters. If you think about 10 to 50 millimeters, it's not that much. But if you then think about if you fall on your bicycle and you hit your head into the ground, that impact is between 5 to 10 milliseconds. And 5 to 10 milliseconds is less than 1/10 of what it takes for you to blink your eye. So then it's a little more challenging. And if you then add that you have a big load on your head, because that is what's happening when you're impacting the head against the ground. You have around 1,000 kilo as a point load during the impact. And then when we talk about this 10 to 15 millimeters, it's a challenge to achieve this during this short duration, during this load. So therefore you need some system, and MIPS is one of these systems that can achieve this. So now we have talked a lot about how we tested in the lab, how we have evaluated, and why we have evaluated. But the important is that it should also work in reality, and therefore we try to better understand how the system work in reality and look into real accidents. So here I would like to give you an example of an accident scenario that happens in a real motocross accident. So this was an accident that happened in Sweden during the Swedish Championship in motocross in 2004. And you see the map of the track here, and the arrow to the left is the leader of the race. And then you have a competitor, the arrow to the right, that's supposed to be turning. So you see on the screen there, he's supposed to be turning downwards on the map, but he gets problem with his bike and continues straight forward and impacting the leader of the race. And it's sad to say, but from a biomechanical perspective, this is a good accident, because you had 2 cameras filming the accident. So based on these 2 cameras, we could estimate the speed of the 2 motorbikes and also see the impact angle. So I will now show you the video from the accident. So you see here is the leader of the race, and shortly you see the person that is impacted. So he gets problem with his motorbike and continues straight forward. This is the person that got impact, so he survived the accident, and here you see it from the other camera view. So you see a massive impact. And just to see it in one time again. The victim of this accident, he sent the helmets to us. So it's actually his helmet that you see. And the red arrows or circles is indicating where the impact occurs on the helmet. And we also know which motorbike it was. So with computer simulation, we reconstructed this accident. And we used the finite element method. And I don't know how many of you knows what finite element method is, but let me take you through a very, very crash course. So the finite element method is used in many different industries. It started in the aviation industry to calculate how the wings of an airplane should be designed to be able to fly. And what we used this methodology to create a model of the human head. And this is done in collaboration with the Royal Institute of Technology here in Stockholm, KTH. So what we do with this finite element method is that we take a big complex problem and divide them into smaller problems. We call them elements. You can see it as small Lego pieces that you put together. And every Lego piece is you define the material properties, if it's brain tissue, if it's a skull, or it's a blood vessel. And then you apply a load to this and see how the different elements deform, and then you can get a response, what happens inside the brain during an impact. And the model includes all the important parts of the brain. But as always, we should remember that a model is always just a model. We need to verify it so we see that it can resemble reality, in this case, a human being. It could be quite difficult because you don't want to perform experiments that is injurious on living tissue. So often what you do is that you do cadaver experiments, and I will show you one example here. So to the left, you will see a video of a cadaver experiments where you have the head and the neck, and you're impacting the surface. And you see also black dots inside the head, and this is tracker that has been inserted into the brain. So you see an X-ray, therefore we can see inside the skull bone. So I will play the video now. So you see these black dots in the brain, and they are moving during the impact. Well, let's look at the video once again. So you see that the markers are moving inside the brain. So you are calculating how much they are moving, and then you apply the same kinematics to the computer model. Now we have locked the FE model, but we see deformation. So red is indicating higher deformation of the brain tissue. So we are then comparing the motion of these markers inside the cadaver and inside the computer model. And we see that we have some realistic response. And this is just one of the markers. We have almost 100 different markers that we can compare to. So this is the model that we have used. So let's go back to this reconstruction of a real accident. So in this case, we also had medical image from the accident. And what we can see here in the medical image to the left, you see a bleeding or hematoma toward the frontal part of the brain. And then you also have to the right, you see another medical image, and you see also bleeding towards the back of the head. So what we did was that we took the medical image and then the results from computer simulation where we looked at the deformation of the brain tissue. You see that to the right, and we see red areas, we see indicating high deformation, so a higher risk of brain injuries, and we see that these red areas are in the same areas where we have the bleeding in the medical image. One thing that's good with simulations is that you can compare, do small modification and see what is the difference. So this simulation was performed with a traditional helmet. So then what we did was that we included a helmet with the MIPS safety system and ran the same simulation and looked at the difference. So here you see the results. So what you see is that you have smaller deformations at the area of injury when including the MIPS safety system. So for us, it's very important to keep the connection to reality. And when you're doing tests in the lab, you are restricted a little by the height of the room. And so the height to the ceiling, so how far we can drop it to get a good impact velocity. So usually in a standardization test, what you're evaluating is impact velocity just below 30 kilometers an hour. But if you think when you're out riding your motorcycle, most probably you're riding higher velocities in urban areas or on motor highways. So our question to ourselves was, how does the MIPS safety system work in this environment, so with higher impact speed? And it's a big challenge to do this test in the lab, so we did simulations. So we did simulation where you had the impact velocity of 130 kilometers an hour. And on the top row, you see the results when having a traditional helmet, not including the MIPS safety system. And on the bottom row, you see when you are including the MIPS safety system. And if we look there to the left, we see the deformation of the brain tissue. Also here, red is indicating higher deformation, higher risk of sustaining a brain injury. So we see less red areas in the lower picture when including the MIPS safety system. So I started to come to the end of the presentation. I will soon hand over to Max, but I just want to show you this last simulation. It's again about rotation, but it's just another way of showing that the brain is sensitive to rotational motion. So we have to the left, we have a straight impact or a linear impact. I will play the simulation here. You see that it's impacting straight. We have not much rotational motion, and we don't have so much deformation of the brain tissue, the blue area there. If I then do the exact simulation, I have the same impact velocity, but impacting with an angle. We look at the deformation. We see that the head starts to rotate, and we see much higher deformation of the brain tissue. So here's another way of showing what was already shown in the 40s, that the brain is sensitive to rotational motion.
Thank you, Madeleine. Great presentation, and of course, a lot of information to take in. So for me, it's really 3 key takeaways that you should take with you from the presentation. So first of all, really important that most accidents include oblique impacts where rotation can be introduced. Hopefully you understand a bit more on the subject. The brain is much more sensitive to rotation rather than linear motion, which most helmet is originally designed to manage. And of course, there is today systems on the market to redirect rotational motion and may provide added safety in many accidents. Of course, listening to the presentation, you get excited. Where can I find a helmet with MIPS? Today, we are in more than 150 different helmet brands in a lot of different kind of sports. If you look at motorcycle specific, then of course we have more than 30 brand partners. So of course also adding more helmet brands all the time, but 30 at the moment. Find the best one and the brand you like and make sure that they have a MIPS equipped helmet. Then of course, if you want to understand more, first of all, go into the MIPS website at mipsprotection.com, where you can understand more on the validation of the technology, what we have done, and of course find your favorite brands. You can also follow us on Instagram at mipsprotection. If there is questions that is not answered during the webinar Q&A, then of course you can always send us an email at info@mipsprotection.com. And with that, we open up for questions.
Okay, so here's the first question from the audience to start off with. If rotation is so dangerous, why aren't more companies talking about it?
I think it's, of course, a difficult subject. We spent more than 30 years to understand it, of course, and something that you see more and more helmet, and you see more and more helmet brands adding technology for rotation. But I would say that, especially in motorcycle, we are still early days.
Okay, so the second question. How do I know if my helmet has MIPS in it?
The easiest way is, of course, to turn on the back side of the helmet. There should be a yellow sticker. We always equip the helmets we are in with a yellow sticker with, of course, the MIPS logo on it. If it doesn't have it, it doesn't carry the MIPS technology.
Does body weight and speed add additional load on rotation?
Maybe you are the best one to answer that.
It's not the easiest question to answer, I would say. So it's depending on the impact situation and so on. But it could influence.
If I crash, when do I need to replace my helmet?
I think in general we always advise that if you had a crash with your helmet, the helmet has normally been worked out, so of course you should go and buy a new helmet. It's a little bit similar like the front hood of your car. If you would crash your car, of course you will go and replace it or go to the repair shop. But the same is for the helmet. The compression zone of the helmet has then normally collapsed at an accident, and then of course you should normally replace the helmet.
Let's see if we have some more questions coming. Yes, now we have one. Any competing technologies in the market?
Yes, there is several competing technologies in the market. There is more than us that think that rotational motion is something to address. So yes, it's available.
Okay, let's see if we have some more questions coming.
So still waiting for more questions. Anything you want to know about MIPS or helmet development in general, just ask a question. We are here for you.
Happy to answer any questions.
I think we say thanks for now then.
Yes, so thank you everyone for listening in. I hope that you learned a lot. And of course, if you have any more questions or didn't want to ask them in the chat box, mail us at info@mipsprotection.com. You could add us to Instagram. There you will get a lot of information about MIPS and of course see all the athletes that we work with. And then of course, if you want to just do a little bit more research on the subject, go into mipsprotection.com to find out more. Thank you. Have a fantastic evening, everyone, and thank you for listening in.